looked at errors and uncertainties. Three main types of errors that we need to know about. Remember, of course, an uncertainty is really how accurate you think your result of an experiment is, or the result of your measurement is. The first of those is random errors. So random errors are really the cause of experimental measurements being different. If you do an experiment, say 5 or 10 times, you're not going to get the same result every single time. The reason for that is because there are random errors there, whether that's because you did something slightly differently, you pushed a button sooner rather than later, you're going to get a spread of results. So we call that a random error. That's what causes this spread of results. So I used an example there of measuring background radiation. If we measure background radiation, say 6 times, we'll get different values every single time because of the random error. But we're trying to eliminate what that random error is by taking more than one value. That's how we can limit the effects of uncertainties. And then what we do after that is we really take an average of those results. And the average of those results can be called the mean. So that's really taking all the values, adding them up and dividing them by the number of readings that are taken. So you probably know it as an average just now. We call it the mean for the purposes of errors and uncertainties. So add all your values together, divide it by the number taken, that's the mean value that you get. So the mean value that we would get for the background radiation there was 21 counts per minute. So that takes into account what the average reading would be. It also has a chance to show up any sort of discrepancies there might be. If there's one value that's much bigger than the other, you can see mistakes much more easily. So it's quite good from that point of view. The more values you take, like say you take 10 or 20, that reduces the random error down and down more and more, because there's going to be more values that are similar to each other. So we asked ourselves the question how accurate the above answer is. It's not 100% accurate, so there's a margin of error within that, and that's what we call the approximate random error. That does take into account the whole spread of results rather than just being an average of the results. So we calculate that by taking the maximum value, taking away the minimum value, and dividing it by the number taken. So we figured out that that was 2 counts per minute was the approximate random error in the mean that we've just calculated. So we can make a statement, we can make a final statement as to what the overall background radiation was. So it would be 21 counts per minute, and it would be plus or minus 2 counts per minute. And as we discussed yesterday, what that means is that the true value of background radiation falls somewhere between 19 and 23. So that's what that plus or minus 2 is. That's the uncertainty within our measurement. So we can't be 100% sure that 21 counts per minute is the answer. So we factor in a margin of error, or an uncertainty, which is plus or minus 2 counts per minute. We've also got systematic errors as well, and that's when you get the same error in all readings. So that makes all your readings either too high or too low. That can be caused by faulty equipment. It's normally faulty equipment. So if you've got a meter stick and you start measuring things from the end of the meter stick as opposed to from the start of the scale, where the scale starts, then all your measurements are going to be out by that tiny wee amount on the front of the meter stick, and that would be a systematic error. We've got reading errors as well. When we're reading off measurements, we've got reading errors on an analog scale, so something like an analog clock or a meter stick. We can be about as accurate as half a scale division. So we can see clearly, say 1 millimeters, 2 millimeters, we can see where the divisions are, but we can only really be accurate to about half a scale division within that. So for an analog scale, we say that there is an uncertainty of plus or minus half a scale division. For a digital scale, we say that plus or minus 1 in the least significant digit. So if it's minutes and seconds, like 0.00, then it would be plus or minus 0.0001, sorry. So plus or minus 1 in the least significant digit for a reading error. So those are your three main types of errors. Random error causes the spread of results experiments to be different all the time. Systematic error, something wrong with the equipment, so all values are either too high or too low. Reading error is when you're actually reading off an instrument. Plus or minus half a scale division for analog, plus or minus 1 in the least significant digit for digital.